Look up at the night sky for just a moment, and you're staring into an infinite ocean of darkness, a cosmic void so vast it defies comprehension. But here's the thing, that darkness isn't empty. It's alive with mysteries we're only beginning to unravel. The universe hides secrets in its shadows, phenomena so strange they challenge everything we think we know. And tonight, we're diving into 25 of the most baffling enigmas lurking in the depths of space. These aren't just scientific curiosities, they're cosmic puzzles that could rewrite the laws of physics, redefine reality, and maybe even answer the oldest question of all: are we truly alone? Picture this, a black hole so massive it warps time itself, a signal from deep space repeating on a loop with no explanation. Galaxies that shouldn't exist, defying the very rules of the cosmos. These aren't scenes from science fiction, they're real, they're out there, and they're waiting to be understood. The cosmic void isn't just a backdrop of stars, it's a stage for the universe's greatest unsolved performances. Some of these mysteries might hold the key to our origins, while others could threaten everything we thought was certain, and the most thrilling part. We're on the brink of uncovering them, so let's take this journey together, because this isn't just about facts or discoveries, it's about the human spirit reaching into the unknown, daring to ask questions that have no easy answers. Each of these 25 mysteries is a piece of a puzzle so grand it spans the entire cosmos. Some will leave you in awe, others might send a chill down your spine, and a few could change how you see the universe forever. By the end, you won't just know more about space, you'll feel it. The wonder, the tension, the sheer scale of what's still waiting to be found. The cosmic void isn't silent, it's whispering its secrets. And tonight we're listening. Somewhere out there, in the blackness between galaxies, something strange is pulling entire clusters of stars at speeds that shouldn't be possible. Scientists call it the dark flow, an eerie cosmic current dragging thousands of galaxies toward some unseen destination, as if the universe itself has a hidden undertow. Normally, gravity explains how things move through space, but this isn't just a gentle drift. These galaxies are racing at over 2 million miles per hour, far faster than any known force could propel them. It's like watching leaves caught in a river's current, except there's no river, no visible source of the pull. What could be yanking galaxies off course? One unsettling theory suggests the presence of another universe beyond our own, a parallel cosmic neighbor whose gravity leaks into ours, tugging at everything in its path. Imagine two soap bubbles barely touching their surfaces, warping just slightly where they meet. Could our universe be brushing up against another, creating this invisible drag? Or perhaps there's something even stranger, a colossal structure we can't see, made of matter or energy unlike anything we've discovered. Some researchers speculate it might be a remnant from the birth of the cosmos, a relic so massive it bends the fabric of space-time itself. Then there's the darker possibility that our understanding of gravity is fundamentally incomplete. Maybe Einstein's equations, which have held true for over a century, break down at scales this vast. It wouldn't be the first time the universe forced us to rewrite the rules, but until we solve the riddle of the dark flow, one thing is certain: the cosmos is hiding forces beyond our imagination, and whatever's out there, whether another universe, undiscovered matter, or new physics, it's rewriting what we thought was possible. Now picture a force so powerful it's dragging hundreds of thousands of galaxies, including our own Milky Way, toward some unseen behemoth lurking behind a cosmic curtain. This is the Great Attractor, a gravitational mystery so colossal it bends the path of everything around it, yet remains nearly invisible to our telescopes. Hidden behind what astronomers call the zone of avoidance, a dense region of stars and dust in our galaxy's plane, this enigmatic powerhouse reveals itself only through its irresistible pull, warping the motion of galaxies across an unfathomable stretch of space. What makes this phenomenon so puzzling isn't just its hidden position, but its staggering scale. the Great Attractor's gravity dominates a region spanning hundreds of millions of light years, pulling galaxies like ours toward it at speeds exceeding 1 million miles per hour. To put that into perspective, our entire local group of galaxies, an unimaginably vast collection of stars, is caught in its current, swept along like leaves in a cosmic wind. At its heart lies the Norma cluster, a dense knot of galaxies that might hold clues to the attractor's true nature, but even that cluster seems too small to account for the sheer strength of this gravitational vortex. Scientists have proposed startling explanations for what could generate such immense power. One leading theory points to dark matter, the invisible scaffolding of the universe accumulated in unprecedented densities, forming a gravitational well deeper than anything we've mapped. Others speculate there might be something even more extraordinary behind it, an intergalactic supercluster so massive it reshapes our understanding of cosmic structures. Recent observations hint at an even larger culprit, the Vela supercluster, a sprawling network of galaxies previously obscured by the zone of avoidance, which could be amplifying the attractor's pull. But here's where the mystery deepens. As we peer through new infrared and radio telescopes that pierce the Milky Way's dusty veil, we're discovering that the Great Attractor might not be the ultimate destination. There's growing evidence that both it and our galaxy are being pulled toward something far more enormous, an inconceivably vast structure nicknamed the Shapley Attractor, lying over 600 million light-years away. This raises an eerie possibility. We might be witnessing a cosmic Russian nesting doll of gravitational anomalies, each one revealing a larger puppeteer behind the last. The implications ripple through our understanding of the universe's structure. If these attractors are signposts pointing to even greater concentrations of mass, they could rewrite the story of how matter clumped together after the Big Bang. Some cosmologists suggest we're seeing the fingerprints of primordial quantum fluctuations, tiny variations in the early universe that snowballed into these gravitational titans. Others wonder if the Great Attractor holds clues to dark energy's greatest rival, a competing force sculpting the cosmos on scales we're only beginning to perceive. What's certain is this: every new observation peels back another layer of the mystery. As next-generation telescopes like the Square Kilometre Array come online, we may finally glimpse the true face of this cosmic leviathan. Until then, the Great Attractor remains a humbling reminder. Even as we map the far reaches of space, some of the universe's grandest designs still lurk in our blind spot, pulling strings we've only just begun to sense. Now imagine stepping into a corner of the universe so desolate, it feels like the cosmos forgot to fill it in. The Boötes Void is a staggering expanse of nothingness, a spherical region nearly 330 million light-years wide where galaxies should be packed wall to wall, yet only a handful linger in the darkness. If our Milky Way sat at its center, we wouldn't have discovered other galaxies until the 1960s. It's like staring into a cosmic donut hole, a blank spot in the starry tapestry, so vast it defies every expectation of how matter should be distributed. How does a void this enormous even form? One leading theory points to the violent aftermath of the Big Bang, where subtle density fluctuations in the early universe left some regions stretched thin while others clumped into galaxy clusters. Over billions of years, gravity amplified these voids as matter migrated toward denser areas, leaving behind caverns of near emptiness. But the Boötes Void is an outlier, far larger and emptier than simulations predict. Some astronomers suggest it might be the result of multiple smaller voids merging, like soap bubbles combining into one gaping pocket of space. Others propose an even stranger idea, that this void isn't empty at all, but filled with something we can't see, dark energy pushing the boundaries of the void outward, accelerating its expansion like an invisible force carving a hole in the universe. Then there's the more speculative explanation, one that sparks the imagination. Could a hyper-advanced civilization have harnessed the energy of entire galaxies, leaving behind a skeletal void? While there's no direct evidence, the concept taps into the Kardashev scale, a framework for hypothetical civilizations capable of engineering on galactic scales. If a Type 3 civilization existed here long ago, perhaps they dismantled stars for energy or constructed structures so vast they altered the fabric of local space-time. It's a tantalizing thought, but the lack of any detectable waste heat or artificial signals makes this more sci-fi than science for now. What's undeniable is the eerie silence of the Boötes Void. The few galaxies that do reside there are oddly isolated, like lone outposts in a desert. Some seem stretched and warped, their light stretched into spectral smears by the void's relentless expansion. This raises another chilling possibility, that the void is still growing, its emptiness pressing outward like a slow-motion shockwave. If so, it could be a preview of the universe's distant future, where dark energy tears apart galaxy clusters until every star stands alone in an ever-cooling abyss. But here's the twist: recent surveys hint that the void might not be as empty as we thought. Ultra-faint dwarf galaxies, barely detectable with current technology, could be lurking in the darkness like ghosts. If confirmed, they might rewrite the story of how voids evolve, revealing a hidden web of matter too dim for our telescopes to see. Until then, the Boötes Void remains one of space's most unsettling enigmas, a whispering reminder that even in a universe crowded with stars, there are places where the night never ends. Consider this staggering fact: our galaxy alone contains hundreds of billions of stars, most with orbiting planets, and many of those worlds sit in the habitable zones where life could thrive. Given these numbers, the universe should be teeming with civilizations. So where is everybody? This glaring contradiction is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked the question during a casual lunch conversation in 1950. The statistics make this mystery even more perplexing. Even if only 1 in a million planets developed intelligent life, there should still be thousands of civilizations in our galaxy. Yet decades of scanning the skies have turned up nothing: no signals, no megastructures, no visiting spacecraft. It's as if the universe is a party where everyone received invitations but no one showed up. One chilling explanation is the Great Filter, some catastrophic barrier that prevents life from advancing beyond a certain point. Maybe the leap from simple cells to complex life is far rarer than we think. Or worse, the filter lies ahead of us, some inevitable catastrophe like nuclear war or runaway artificial intelligence that wipes out civilizations before they can spread across the stars. Then there's the zoo hypothesis, the idea that advanced civilizations deliberately avoid contact, observing us like animals in a cosmic wildlife preserve. It would explain the silence but raises unsettling questions. Who are the zookeepers, and what rules might they impose on species like ours? Other theories are even wilder. Some suggest we're alone in a simulation, the rest of the universe just an elaborate backdrop. Others propose that aliens have visited, but in forms we simply can't recognize: dimensional beings or artificial intelligences operating on timescales beyond human comprehension. One thing is certain: the Fermi Paradox forces us to confront the fragility of intelligence. Whether the answer lies in physics, biology, or something beyond our current understanding, it remains one of the most profound puzzles in science. And until we solve it, the stars remain eerily silent. One moment the cosmos is silent, the next a blinding flash of radio energy erupts across the universe, packing more power than 500 million suns, then vanishes in less than a blink. Fast radio bursts are among the most violent and mysterious phenomena in the cosmos, fleeting signals that hit our telescopes like cosmic lightning strikes, leaving astronomers scrambling for answers. First discovered in 2007, these bursts last mere milliseconds, yet their energy dwarfs anything we've seen before. And the strangest part: no one knows what's causing them. Some bursts appear randomly, one-time cosmic screams echoing from the void. Others repeat on erratic schedules, like a celestial alarm clock with no rhyme or reason. One particularly famous repeater, catalogued as FRB 121811, has been flashing intermittently since 2012, its signal traveling 3 billion light-years to reach us. The distance alone is staggering, but what's truly baffling is how these bursts maintain their intensity across such vast stretches of space. Any normal signal would dissipate, scattering into noise. Yet FRBs arrive crisp and clear, as if something or someone is focusing their energy with precision. The leading theory points to magnetars, neutron stars with magnetic fields so powerful they could strip the electrons from your atoms at 1,000 miles away. When these exotic stars experience starquakes, violent ruptures in their crusts, they might unleash bursts of radiation capable of explaining some FRBs. In 2020, astronomers even caught a magnetar in our own galaxy emitting a FRB-like signal, lending weight to the idea. But there's a problem. Not all bursts fit this explanation. Some are too powerful, too frequent, or originate from regions of space where no magnetars have been detected. This opens the door to wilder possibilities. Could colliding neutron stars or evaporating black holes generate these flashes? Some models suggest exotic physics like cosmic strings, theoretical defects in space-time snapping and releasing energy. Then there's the elephant in the room. Could we be detecting artificial signals? The precision and power of FRBs have led a handful of scientists to speculate about advanced civilizations harnessing energy on a galactic scale. Imagine a propulsion system shooting focused beams across the cosmos, or a beacon designed to shout across the universe. While there's no direct evidence for extraterrestrial origins, the sheer engineering required to produce such bursts would imply technology far beyond our own. Yet the most unsettling aspect of FRBs isn't their source, it's their distribution. These bursts aren't clustered in any recognizable pattern. They come from everywhere, as if the universe itself is peppered with invisible flashbulbs. Recent studies suggest we might be detecting only a fraction of them, with thousands potentially flashing every day unseen. If that's true, we're witnessing just the tip of a cosmic iceberg, a hidden layer of reality pulsing beneath our notice. New telescopes like the Canadian Chime Array are revolutionizing our ability to catch these elusive bursts, sometimes spotting dozens in a single month. Each detection peels back another layer of the mystery, revealing subtle variations in polarization, frequency, and dispersion. Some bursts even exhibit bizarre sub-patterns, like a coded message hidden in static. Whether natural or artificial, one thing is certain: FRBs are forcing us to rethink what's possible in the universe. They're not just cosmic oddities, they're flares in the darkness, signaling secrets we've yet to decode. Every millisecond burst is a reminder: the universe is stranger, louder, and far more mysterious than we ever imagined. Late one summer night in 1977, a radio telescope in Ohio picked up something extraordinary: a 72-second burst of radio waves so powerful and unusual that an astronomer scrawled, "Wow," in red ink on the printout, giving the signal its now famous name. What made this detection so remarkable wasn't just its strength, 30 times louder than the cosmic background noise, but its frequency. The signal hit exactly 1,420 MHz, a quiet band of the spectrum where natural cosmic phenomena rarely emit, but one that interstellar civilizations might logically use for communication. It was as if the universe had shouted directly at us, then immediately clammed up. Decades later, the wow signal remains astronomy's most tantalizing might have been. The signal's structure held all the hallmarks of an artificial transmission narrowband, focused and drifting in frequency just as you'd expect from a distant planet rotating beneath a fixed transmitter. Yet despite exhaustive searches of that same patch of sky in Sagittarius, the signal never repeated, not once. It's like hearing a single, crystal-clear word whispered in a crowded room, then spending the rest of your life straining to hear it again over the chatter. Theories about its origin range from the mundane to the extraordinary. Some suggest a passing comet might have reflected earthly radio noise back to us, but follow-up calculations show known comets weren't in the right position. Others propose an exotic astrophysical event, a previously unknown type of quasar flare or neutron star oscillation, but nothing since has matched its unique profile. Then there's the obvious but unsettling possibility. We caught a one-time beacon from an advanced civilization, perhaps a test signal or distress call that swept past Earth by chance. What makes the WOW signal uniquely frustrating is how it straddles the line between detection and mystery. Unlike fast radio bursts which arrive by the dozens, this was a singular event with no obvious natural explanation. Modern SETI projects like Breakthrough Listen now monitor millions of frequencies simultaneously, but in 1977, telescopes could only scan one channel at a time. That means the WOW signal might not have been alone. We could have missed companion transmissions that would have revealed its true nature. The signal's legacy endures not just as a cosmic riddle, but as a lesson in scientific humility. It taught us how ill-equipped we were to recognize extraterrestrial communication, prompting upgrades in telescope sensitivity and data analysis. Recent attempts to explain it using contemporary astrophysics keep falling short, which leaves open that spine-tingling alternative, that for 72 seconds in 1977 we weren't alone in the universe. And somewhere out there, buried in the static of space, the truth still waits. At the frozen edge of our solar system, where sunlight is a faint memory and temperatures plunge near absolute zero, something bizarre happens. The Kuiper Belt, a sprawling ring of icy debris left over from the solar system's birth, suddenly stops. Not with a gradual fade, but with a sharp, unexplained boundary astronomers call the Kuiper Cliff. Beyond this invisible line, the number of objects drops by more than 99%, as if someone erased the outer solar system with a cosmic eraser. This isn't just a curiosity, it's a violation of everything we know about how planetary systems form. The Kuiper Belt should thin out slowly, with smaller objects lingering farther from the Sun. Instead, it's like reaching the edge of a cliff where the rocks simply vanish. The most plausible explanation: gravity from something massive we haven't found yet. A hidden planet, perhaps 5 to 10 times the size of Earth, lurking in the darkness beyond Pluto, could be shepherding objects away with its gravitational pull. Astronomers have even given this hypothetical world a name, Planet 9, but here's where it gets stranger. The Kuiper Cliff isn't just empty, it's sculpted. Some objects near the boundary orbit at extreme angles, as if they were knocked off course by a powerful disturbance. That's led to competing theories. Maybe Planet 9 isn't the culprit at all. Instead, the solar system might have had a violent past, a close encounter with a rogue star or a long-lost sibling planet that was ejected, tearing through the Kuiper Belt like a bull in a cosmic china shop. Simulations show either scenario could explain the abrupt edge, but proof remains elusive. Then there's the dark horse theory. The cliff isn't physical at all. Some researchers suggest we're seeing an observational blind spot, where current telescopes simply can't detect smaller, more distant objects. New surveys like the Vera Rubin Observatory aim to settle this. If they find a hidden population of icy bodies beyond the cliff, the mystery might vanish. But if they confirm the drop-off is real, the implications are profound. Either way, the Kuiper Cliff forces us to confront how little we truly know about our own cosmic backyard. The search for answers is heating up. Every new survey of the outer solar system brings us closer to understanding whether we're missing a planet, witnessing scars from an ancient catastrophe, or staring at a flaw in our own assumptions. One thing's certain: the edge of the solar system isn't just a boundary, it's a puzzle waiting to be solved. And its solution might rewrite the story of how our cosmic neighborhood came to be. In October 2017, astronomers spotted an object hurtling through our solar system at nearly 200,000 miles per hour. But this wasn't just another asteroid. Named Oumuamua, Hawaiian for Scout, it was the first confirmed visitor from interstellar space, and it behaved like nothing we'd ever seen. Its trajectory was too extreme to be bound by the sun's gravity, and its speed suggested it had been drifting between stars for millions of years. But the real shock came when researchers realized Oumuamua wasn't just passing through. It was accelerating as if pushed by an unseen force. The anomalies piled up. Most comets speed up when sunlight vaporizes their ice, creating a visible tail, but Oumuamua had no such tail. Its brightness fluctuated wildly, suggesting an elongated, tumbling shape, perhaps 10 times longer than it was wide, like a cosmic cigar. No natural object we've observed matches this profile. Even stranger, its acceleration didn't follow the usual patterns of outgassing, leaving scientists scrambling for explanations. Some proposed exotic ices turning directly to gas in the vacuum of space, while others wondered if solar radiation pressure could account for the push, but the numbers never quite added up. This peculiar behavior sparked a more radical theory. What if Oumuamua wasn't a natural object at all? Astronomer Avi Loeb famously suggested it might be artificial, a light sail from an advanced civilization designed to harness starlight for propulsion. The idea wasn't entirely far-fetched. Human projects like Breakthrough Starshot aim to send tiny light sails to nearby stars within decades. Could Oumuamua be someone else's version, drifting derelict? The lack of radio signals dampened hopes, but the possibility lingered. We might have witnessed our first piece of interstellar technology floating silently past Earth. Mainstream astronomy leans toward natural explanations, though even these require rewriting the rules. One study proposed Oumuamua could be a shard of a Pluto-like planet, ripped away by a distant collision and rich in nitrogen ice that vaporized invisibly. Another suggested it was a fractal-like dust bunny formed in the chaotic environment around a newborn star, but each theory has holes. Nitrogen ice would require an implausibly large parent body, while fractal structures shouldn't survive interstellar travel intact. The most frustrating part, we'll likely never know for sure. Oumuamua sped out of telescope range before its full nature could be pinned down, becoming a permanent cosmic riddle. Yet its legacy endures. Future telescopes like the Vera Rubin Observatory will scan for more interstellar visitors, ready to capture them before they vanish. Whether Oumuamua was a weirdly shaped rock or something far more extraordinary, it taught us a vital lesson. The universe is full of surprises, and some might be sailing right through our backyard. The universe is supposed to be indifferent to our existence, a vast, structureless expanse where no direction holds special meaning. That's the Copernican principle, the foundation of modern cosmology, telling us we don't occupy a privileged place in the cosmos. But when scientists mapped the afterglow of the Big Bang, they stumbled onto something that shouldn't be there, an eerie alignment in the fabric of reality itself. They called it the axis of evil, and its existence threatens to unravel everything we thought we knew about the universe's structure. This cosmic anomaly lurks in the cosmic microwave background, the faint radiation left over from the universe's infancy. When satellites like Planck and WMAP created ultra-precise maps of this primordial light, they expected random fluctuations, tiny variations in temperature revealing the seeds of future galaxies. Instead, they found something unnerving. These fluctuations weren't entirely random. They aligned along a specific axis that bizarrely coincides with the plane of our solar system. It's as if the universe left a fingerprint and it's pointing directly at us. The implications send shivers through the astrophysics community. If the universe has a preferred direction, an axis where its fluctuations line up, it challenges the core assumption that the cosmos is uniform and isotropic. That would mean we might, in fact, occupy a special place, a thought so heretical in modern science that many researchers initially dismissed the alignment as a fluke or measurement error. But the more data we collect, the harder it becomes to ignore. The odds of this happening by chance are less than 1 in 1,000, a statistical red flag waving in the face of conventional cosmology. Explanations range from the mundane to the mind-bending. Some suggest local interference, dust in our galaxy, or instrumental artifacts distorting the signal. Others propose deeper physics at play. Perhaps dark energy or undiscovered quantum effects imprinted this pattern during the universe's first moments. The most radical idea, that we're seeing evidence of a pre-Big Bang universe, a cyclic cosmos where past iterations left scars on the fabric of space-time. Yet the simplest interpretation is also the most unsettling, that the universe isn't as indifferent to us as we believed. If the axis of evil holds up under even sharper scrutiny from next-generation telescopes, it could force a scientific revolution as profound as Copernicus's own. After centuries of assuming we're cosmic nobodies, we might have to confront the spine-tingling possibility that the universe, in some way we don't yet understand, is looking back at us. For decades, whispers have circulated about an object silently circling our planet, not one of our own satellites, but something far older, perhaps watching us since before human civilization began. The Black Knight satellite legend claims this mysterious craft has orbited Earth for 13,000 years, transmitting signals and appearing in historical accounts long before the space age. The story weaves together grainy NASA photographs, alleged radio transmissions, and even references in Nikola Tesla's notes to paint a picture of extraterrestrial surveillance. But peel back the layers and you'll find a tale where science fiction and misunderstood reality collide. The myth gained traction in 1960 when newspapers reported a mysterious dark object detected by radar, seemingly trailing the newly launched Discoverer 8 satellite. Tabloids ran wild with theories of alien origin, but the truth was far simpler. Space debris from earlier missions, possibly a thermal blanket lost during an astronaut's repair. What conspiracy theorists call photographic evidence often turns out to be images of discarded insulation or camera straps floating near the International Space Station. Even the notorious 1998 Space Shuttle Endeavour footage showing a dark, tumbling object often cited as the Black Knight was later confirmed as a lost thermal cover. Then there's the supposed ancient connection. Proponents claim the Black Knight appeared in medieval woodcuts or Norse legends, but historians point out these interpretations rely on creative readings of symbolic art. One often cited example, a carving in France's Chartres Cathedral, actually depicts a biblical angel holding a celestial orb, not a high-tech satellite. The legend's persistence reveals more about human psychology than cosmic mysteries. We're wired to see patterns even where none exist, especially in the vast and unfamiliar frontier of space. Yet the most intriguing twist comes from a real scientific oddity. In 1927, radio pioneers like Norway's Georgian House detected eerie long-delay echoes, signals bouncing back seconds after transmission as if reflected by something in orbit. While ionospheric conditions could explain these anomalies, the timing fueled speculation about an artificial object amplifying the signals. Modern researchers attribute the phenomenon to plasma interacting with Earth's magnetic field, but the mystery remains a rare instance where legitimate science briefly intersected with the Black Knight myth. Today, astronomers track thousands of defunct satellites and rocket fragments circling Earth. None exhibit the Black Knight's purported characteristics. Radar sweeps by agencies like NORAD have never detected an unaccounted for object matching its description. Still, the legend endures because it touches on a deeper truth. Space is filled with unknowns, and sometimes the line between debris and discovery depends on where you choose to look. Whether a modern myth or evidence of something yet unexplained, the Black Knight reminds us that even in our own celestial backyard, mysteries still linger. Here's a cosmic accounting error that keeps astrophysicists awake at night. When you tally up all the stars, galaxies, and gas clouds we can observe, you're still missing nearly half the normal matter that should exist in the universe. This isn't dark matter. That mysterious substance makes up 25% of the cosmos, but the ordinary atoms that form everything we see, touch, and are made of. Scientists call this the missing baryon problem, and it's like discovering half the ingredients for a cake simply vanished from your kitchen mid-recipe. So where did all this matter go? The leading theory points to an invisible cosmic highway, a network of ultra-diffuse gas filaments stretching between galaxies, too faint and hot for traditional telescopes to spot. These threads, part of the so-called warm-hot intergalactic medium, would form a scaffolding between galaxy clusters like cobwebs glistening with dew in the dawn light. The gas here is scorching up to 1,000,000 degrees, which means it doesn't emit visible light, only subtle X-rays that require specialized detectors to observe. Recent breakthroughs support this idea. In 2017, astronomers using the ESA's XMM Newton telescope found signatures of this long-sought gas in the tendrils connecting galaxy clusters Able 133 and Able 89, finally spotting traces of the missing baryons. But there's a twist. Even accounting for these faint filaments, the numbers still don't fully add up. Some researchers propose alternative hideouts, enormous reservoirs of cold gas in cosmic voids, or matter bound up in rogue planets and brown dwarfs drifting unseen between stars. Others suggest more exotic explanations. Could some baryons have decayed into unknown particles over billions of years? The most radical idea involves leakage into other dimensions through quantum foam, though this remains speculative. The stakes are higher than they seem. Solving this mystery isn't just about balancing cosmic books, it's about verifying our understanding of how the universe organizes itself. These missing atoms are the raw material for stars, planets, and life itself. If we've misjudged their distribution, we might need to rethink how galaxies form and evolve. New instruments like the upcoming Athena X-ray Observatory aim to map these hidden gas currents in unprecedented detail, potentially closing the gap in our cosmic inventory. Until then, the missing baryons stand as a humbling reminder. Even the ordinary stuff of the universe has secrets left to reveal. When NASA Pioneer 10 and 11 spacecraft ventured beyond Saturn in the 1980s, mission scientists expected their trajectories to follow Newton's laws with pinpoint precision. Instead, something bizarre happened. Both probes began slowing down slightly more than calculations predicted, as if an invisible hand were gently tugging them backward toward the sun. This tiny discrepancy, just a fraction of a nanometer per second squared, became known as the Pioneer Anomaly, and for decades it haunted physicists as a potential crack in our understanding of gravity. At first glance, the numbers seemed trivial, a drift of about 300,000 miles over 20 years. But in the precise world of orbital mechanics, where spacecraft navigation relies on equations refined over centuries, even microscopic deviations demand explanation. The anomaly sparked fierce debate. Was this evidence of new physics, like modifications to Einstein's general relativity or the gravitational pull of unseen dark matter? Or could mundane forces aboard the probes themselves, a whisper of heat escaping their radioactive power sources, be nudging them off course? The thermal explanation gained traction as engineers meticulously reconstructed the Pioneer's heat signatures. Every watt of energy radiating from their plutonium-powered systems could, in theory, create enough recoil to account for the deceleration. By 2012, a landmark study analyzing decades of telemetry data concluded that asymmetrical heat flow, warmth leaking preferentially from one side of the craft, matched the anomaly almost perfectly. Case closed, not quite. Skeptics pointed to lingering inconsistencies. If heat alone explained the effect, why did other spacecraft with similar designs, like the Galileo and Ulysses probes, show no such drift? And why did Pioneer's anomaly persist even as its power output decayed over time? Some theorists proposed exotic alternatives, like quantum vacuum fluctuations exerting subtle drag, or the universe having a faint, undiscovered, frame-dragging effect that alters motion at cosmic scales. The most tantalizing possibility was that the Pioneer anomaly hinted at modified Newtonian dynamics, Ormond, a controversial theory suggesting gravity behaves differently at extremely low accelerations. If true, it could upend our need for dark matter to explain galactic rotations. Yet when the New Horizons probe reached Pluto in 2015 with instruments far more precise than Pioneer's, it detected no similar anomaly, dealing a blow to human credibility. Today, the consensus leans toward the thermal answer, but the debate left an indelible mark on physics. It underscored how even the tiniest discrepancies can drive scientific revolutions or reveal unseen complexities in systems we thought we understood. The Pioneers, now silent and drifting toward interstellar space, may have delivered their most profound lesson not in their data but in their defiance. Sometimes the universe's quietest whispers force us to listen closest. Among all the cosmic structures we've discovered, few are as geometrically perfect or as baffling as the Red Rectangle Nebula. Floating 2,300 light-years away in the constellation Monoceros, this glowing, crimson-hued structure earned its name from the near-perfect lines and sharp angles that define its shape. But the real shock comes when you peer closer. At its heart lies a dazzling X-shaped pattern, as if some celestial architect drafted it with a ruler. Most planetary nebulae, the glowing shells of gas expelled by dying stars, form chaotic, bubble-like structures. So how did this one end up looking like a piece of cosmic origami? The answer might lie in the nebula's hidden dance partner. Unlike solitary stars like our Sun, the central star here, HD 44179, is actually part of a binary system. For centuries, these two stars have been locked in an intimate orbital embrace, their gravitational waltz shaping the nebula's extraordinary symmetry. As the primary star bloated into a red giant near the end of its life, its outer layers spilled into space, but instead of expanding evenly, the companion star's gravity funneled the material into two opposing cones. Imagine squeezing a tube of toothpaste from both ends at once, creating twin jets that collide and flatten into that iconic X shape we see today. Yet the geometry alone doesn't explain the nebula's eerie glow. The red rectangle isn't just red, it's saturated with complex organic molecules called polycyclic aromatic hydrocarbons, or PAH. These carbon-rich compounds, often found in soot or engine exhaust on Earth, catch and scatter starlight in ways that paint the nebula with its distinctive crimson hue. Even stranger, the dust here seems to form microscopic hexagonal platelets, like infinitesimal snowflakes aligned in perfect formation. Some researchers speculate these could be precursors to probiotic molecules, the cosmic building blocks that might seed life elsewhere in the universe. Then there's the puzzle of timing. Most planetary nebulae last only tens of thousands of years before dispersing into the void, a blink in cosmic terms. But infrared observations suggest the red rectangle might be far older, its structure preserved by some unseen mechanism. One theory suggests the binary system's precise balance acts like a metronome, steadily replenishing the nebula with fresh dust and gas to maintain its crisp edges. Others propose magnetic fields, invisible and unbreakable, might be holding the shape together like cosmic stitching. But perhaps the most mesmerizing detail is what lies ahead. In a few thousand years, the central stars will finish their dance, leaving behind a dense white dwarf surrounded by fading embers. By then, the red rectangle's perfect geometry will have unraveled, its dust scattered to birth new stars and planets. For now, though, it stands as a fleeting masterpiece, a reminder that even in death, stars can create beauty beyond imagination, and that the universe has a way of turning chaos into symmetry when we least expect it. In the constellation Cygnus, 1,300 light-years from Earth, a star named KSE 8462852 behaves like no other. Astronomers know it better as Tabby's star, nicknamed after Dr. Tabitha Boyajian, who first documented its bizarre flickering in 2015. What makes this star so extraordinary isn't just that it dims. All stars fluctuate slightly, but the sheer drama of its dips. While most stars fade by fractions of a percent, Tabby's star plunges by up to 22% at irregular intervals, as if something colossal is passing in front of it. And the plot thickens. These dimming events aren't periodic. They strike at random, lasting days or weeks, then vanish without warning. Initial explanations pointed to natural causes. A swarm of comets, for instance, could theoretically block starlight as they disintegrate near the star. But the numbers didn't add up. To create dips this severe, you'd need hundreds of thousands of giant comets, an implausible army of icy bodies far exceeding anything in our solar system. Another idea involved dense patches of interstellar dust drifting across our line of sight. But observations from the Spitzer and Hubble telescopes showed the dimming affects some wavelengths more than others, a fingerprint that doesn't match typical dust behavior. This is where things get wild. In 2016, astronomer Jason Wright proposed a radical alternative. What if we're seeing artificial megastructures? Specifically, a Dyson swarm, a hypothetical array of energy-collecting panels built by an advanced civilization to harness their star's power. The irregular, deep dimming could align with massive constructs in various orbits, their uneven shapes blocking light unpredictably. It's a staggering idea, one that ignited media frenzy and rigorous scientific debate. Even skeptics admitted the data warranted investigation, leading to breakthrough LISTEN's radio scans for potential technosignatures. So far, silence, but the absence of signals doesn't rule out engineering on a scale beyond our detection. Recent observations have peeled back more layers without settling the mystery. In 2021, Tabby's star unexpectedly brightened for months, then dimmed again in ways that defied predictions. Spectroscopic studies revealed the star isn't just dimming, it's also gradually fading over decades, losing brightness at a rate that's left astrophysicists scratching their heads. Some suggest it's recovering from a cataclysmic collision with a planet, while others point to internal stellar processes we don't yet understand. The most compelling twist: Tabby's star isn't alone. Astronomers have since identified dozens of similar dipper stars, each with erratic light curves that resist easy explanation. Whether natural or artificial, these objects hint at phenomena darker and stranger than we've imagined. For now, Tabby's star remains an enigma, a cosmic detective story where every clue leads to deeper questions. It challenges us to confront the limits of our knowledge and to wonder, in a universe full of shadows, how many are cast by something we've yet to dream of. Hidden among the constellations Hercules and Corona Borealis lies a structure so vast it shouldn't exist, a sprawling filament of galaxies stretching an incomprehensible 10 billion light-years from end to end. This is the Hercules Corona Borealis Great Wall, a cosmic behemoth so massive it defies the very rules of how the universe organizes matter. To put its scale into perspective, if you traveled at the speed of light, it would take you twice the age of Earth just to cross it. The existence of such a colossus throws into question one of cosmology's fundamental principles, the idea that at large enough scales, the universe should look roughly the same in every direction. What makes this Great Wall so unsettling isn't just its size, it's the timing. According to our current understanding of cosmic evolution, structures this enormous shouldn't have had enough time to form after the Big Bang. The universe is only 13.8 billion years old, yet here we have a galactic superstructure that spans nearly 3/4 of that distance. It's like finding a 1,000-story skyscraper in the middle of the Bronze Age, something that, by all rights, shouldn't be possible given the era. The discovery came in 2013 when astronomers mapping gamma-ray bursts, the brightest explosions in the universe, noticed an eerie pattern. These bursts weren't scattered randomly across the sky. Instead, they clustered along what appeared to be an invisible scaffolding, tracing the outline of something far larger than any known galaxy cluster or supercluster. Follow-up observations confirmed the terrifying scale of this formation, with galaxies and dark matter bound together by gravity in a thread so vast it challenges the cosmological principle, the bedrock assumption that the universe is homogeneous at grand scales. Now, scientists face a dilemma. Either our models of cosmic structure formation are missing something fundamental, perhaps flaws in how we understand dark matter's role or the influence of dark energy, or the Hercules Corona Borealis Great Wall is evidence of something even more extraordinary, an imprint from the universe's birth. Some theorists speculated it could be a remnant of quantum fluctuations from inflation, those first moments when the cosmos expanded exponentially faster than light. If true, this wall might be a fossil from the dawn of time itself, a ripple frozen into the fabric of space before galaxies even existed. Yet the mystery deepens with recent observations suggesting the wall might not be alone. Other ultra-large structures, like the Sloan Great Wall and the South Pole Wall, hint that the universe might favor building on scales we once thought impossible. Each new discovery pushes the boundaries of what we consider plausible, forcing us to question whether the cosmic web is far more intricate and far stranger than we ever imagined. The Hercules Corona Borealis Great Wall stands as a humbling reminder that the universe still holds surprises capable of rewriting textbooks. Whether it's a flaw in our models, a glimpse of deeper physics, or simply the first of many cosmic giants waiting to be found, one thing is clear: the cosmos refuses to play by the rules we've set for it. And in that refusal lies the thrill of discovery, the chance to peel back another layer of the universe's grand design. In the grand tapestry of the cosmic microwave background, the afterglow of the Big Bang, one patch of sky stands out like a chilling blank spot on an otherwise bustling map. Nestled in the constellation Eridanus, this cold region spans nearly 2 billion light-years, a staggering absence of galaxies so vast it's been dubbed the Eridanus supervoid. But here's what's truly unsettling. This isn't just an empty corner of space. It's a cosmic refrigerator, cooling photons from the early universe as they pass through, leaving a detectable chill in the very fabric of reality. When scientists first spotted this anomaly in data from the Wilkinson Microwave Anisotropy probe, they assumed it was a glitch. After all, the cosmic microwave background should be uniformly speckled with tiny temperature variations, relics of quantum fluctuations from the universe's infancy. Instead, they found a cold spot up to 70 microkelvin cooler than its surroundings, a discrepancy far beyond statistical noise, the most plausible explanation. A void, not just any void, but one of the largest structures ever observed, a bubble of near-nothingness where matter is so thinly spread that photons lose energy as they traverse it, stretching to longer, cooler wavelengths in a process called the integrated Sachs-Wolf effect. But the plot thickens. Simulations suggest a void this size should be extraordinarily rare in our standard model of cosmology, so rare that some researchers argue it might not be a void at all. Enter the multiverse hypothesis. Could this cold spot be a bruise left by a collision with another universe? The idea isn't as far-fetched as it sounds. If our cosmos is one bubble in an eternal inflationary multiverse where other universes bubble up endlessly, then a grazing impact from a neighboring universe could have pushed matter away, leaving behind this cosmic dent. Supporters point to the cold spot's unusual shape, slightly elongated, as if something had pressed into it, as potential evidence. Skeptics counter with Occam's razor. Perhaps we're simply seeing a statistical fluke amplified by selection bias, or a superposition of smaller voids that only appear colossal from our vantage point. Newer surveys, like those from the Planck satellite, have added fuel to the debate. While they confirm the cold spot's existence, they also reveal subtleties in its polarization patterns that don't perfectly align with void predictions. The truth might lie somewhere in between, a rare but natural underdensity magnified by quirks in how we observe it. What makes the Eridanus supervoid so compelling isn't just its size or temperature, but what it represents, a stress test for our understanding of the cosmos. If it's a void, it challenges models of how structure forms. If it's a multiverse signature, it rewrites our place in reality. And if it's neither, then the universe still has secrets we've yet to imagine. As next-generation telescopes like the Simons Observatory train their sights on this enigmatic cold spot, one thing is certain: the void isn't empty, it's full of questions. Deep in the constellation Cetus, a galaxy is breaking all the rules. NGC 1052DF2 looks like any other faint, diffuse galaxy until you realize something fundamental is missing. This cosmic outlier appears to contain almost no dark matter, the invisible scaffolding that supposedly binds every galaxy together. It's like finding a skyscraper standing tall without any steel beams, defying everything we thought we understood about how the universe builds its structures. The discovery sent shockwaves through astrophysics when announced in 2018. Dark matter isn't just a minor ingredient, it's thought to outweigh visible matter 5-to-1, sculpting galaxies with its gravitational pull. Yet measurements of DF2's rotation showed stars moving at speeds explainable by normal matter alone. Follow-up studies using the Hubble Space Telescope confirmed the anomaly. This galaxy's mass was concentrated in its stars and gas, with dark matter contributing at most 1/400th the expected amount. How could such a galaxy form? One possibility is a violent past. Perhaps DF2 was stripped of its dark matter in a catastrophic collision. Simulations show when two galaxies merge, the diffused dark matter halo can be flung outward while the dense stars remain. But DF2 shows no signs of disruption. Its pristine disk suggests a quieter history. Another theory suggests it formed from gas expelled during a galactic pile-up, condensing into stars without the usual dark matter foundation. Then there's the more radical interpretation. Maybe dark matter isn't universal after all. A few maverick physicists see DF2 as evidence for modified gravity theories like MUND, which eliminate dark matter by tweaking how gravity behaves at cosmic scales. If gravity strengthens slightly where accelerations are tiny, as in a galaxy's outskirts, it could mimic dark matter's effects without requiring invisible particles. Yet MUND struggles to explain all of DF2's quirks, leaving most cosmologists favoring dark matter's existence while puzzling over this outlier. Measurement errors offer the simplest solution. Some astronomers argue DF2 might be closer than estimated, making its motions appear slower and reducing the inferred dark matter deficit. Others suggest its unusual globular clusters, extremely bright and massive, could be skewing the calculations. But subsequent discoveries of similar dark matter-deficient galaxies, like DF4, suggest DF2 isn't a fluke. Whether cosmic exception or clue to new physics, NGC 1052DF2 forces us to confront an uncomfortable truth. Our models of galaxy formation might be missing a crucial chapter. It stands as both a challenge and an invitation, a cosmic rebel demanding we rethink the invisible forces shaping our universe. Picture stepping outside on a clear, moonless evening just before dawn or after sunset. If conditions are perfect, you might spot an eerie, faint glow stretching upward from the horizon, a soft cone of light often mistaken for twilight. This is the zodiacal light, sunlight scattered by countless dust particles drifting between the planets, and it's been part of our sky since antiquity. But modern measurements reveal something odd. This glow is up to 10 times brighter than it should be, given the known dust in our solar system. It's as if the universe left a lamp on and no one can find the switch. The source of this excess light has puzzled astronomers for decades. Traditional models point to dust from comets and asteroid collisions, fine debris ground down over billions of years, slowly spiraling toward the sun. But when you tally up all the dust these processes should produce, the numbers fall embarrassingly short. One theory suggests hidden reservoirs of dust might lurk in poorly explored regions like the Kuiper Belt or the Oumuamua cloud, releasing fresh particles through collisions we haven't yet observed. Another possibility involves interstellar dust, fine grains drifting in from neighboring star systems, adding their faint sparkle to the mix. Yet even accounting for these sources, the math still doesn't quite balance. Then there's the human factor. Since the mid-20th century, rocket launches and satellite deployments have littered Earth's orbit with debris, some of which may be vaporizing into microscopic shards under solar radiation. Could space-age pollution be amplifying the zodiacal light? Studies show that aluminum and other spacecraft materials do scatter sunlight efficiently, but estimates suggest their contribution is negligible compared to the overall discrepancy. Still, it's a haunting thought our own technology might be quietly altering the sky's natural glow in ways we're only beginning to measure. The most tantalizing explanation lies closer to the sun. Recent simulations hint at a previously overlooked population of dust particles trapped in stable orbits near Mercury's path, heated to extreme temperatures but never falling in. These volcanoid particles, if they exist, would glow intensely under the sun's glare, potentially accounting for the missing brightness. The trouble: no telescope has definitively spotted them. Solar observatories like NASA's Parker Solar Probe are now hunting for this elusive dust, skimming closer to the sun than any spacecraft before, searching for the faint shimmer that might solve the mystery. What makes this enigma so compelling isn't just the missing dust, it's what that dust implies. These particles are more than celestial clutter. They're fossils from the solar system's violent youth, remnants of the collisions that built our planets. If we've underestimated their abundance, we might be missing clues about how Earth itself formed. Or perhaps the discrepancy points to something even stranger, an undiscovered population of microcomets or exotic physics affecting how dust interacts with sunlight. For now, the zodiacal light continues to shine brighter than our models predict, a gentle reminder that even in our own celestial neighborhood, the cosmos keeps secrets. As new telescopes and space missions refine our measurements, we may finally pinpoint the source of this ghostly glow. Until then, it stands as a testament to an enduring truth. Sometimes the most familiar sights in the night sky hold the deepest mysteries. Tucked away in the constellation Monoceros, the celestial unicorn, lies a cosmic paradox that defies expectations. Just 1,500 light-years from Earth, practically next door in galactic terms, astronomers have identified what appears to be the smallest known black hole, weighing in at just 3 times the mass of our Sun. They've named it the Unicorn, not just for its home constellation, but for how improbably elusive it proved to be. This discovery didn't come from spotting the black hole itself. As always, these gravitational traps are invisible, but by watching the subtle dance of a nearby red giant star. The star's light stretches and compresses rhythmically, as if an unseen partner tugs at it with clockwork precision. After ruling out other explanations, researchers realized only one thing could exert such a tight gravitational grip while remaining unseen. A black hole so lightweight it straddles the theoretical boundary between what can form from a dying star and what collapses into a neutron star instead. What makes the unicorn so revolutionary isn't just its size, it's what its existence implies about the cosmos. Conventional models suggested black holes below 5 solar masses were exceedingly rare if they existed at all. Stars that light typically collapse into neutron stars, those ultra-dense remnants that pack a sun's worth of mass into a city-sized sphere. Yet here's the unicorn, defying the odds and raising a provocative question. Could there be an entire population of these tiny black holes we've overlooked? The detection method used here, analyzing distortions in a companion star's motion, is painstaking work, requiring years of precise measurements to disentangle the black hole's influence from other stellar phenomena. If similar objects are hiding in binary systems across the galaxy, we might be missing a silent majority of black holes simply because we weren't looking for something so small. The hunt for these diminutive monsters isn't just academic. Finding more unicorns could solve one of astrophysics' most stubborn puzzles, the so-called mass gap problem. For decades, astronomers have noticed a curious absence of compact objects between the heaviest neutron stars, around 2.2 solar masses, and the lightest confirmed black holes, around 5 solar masses. Some theories suggested this gap might be fundamental, a quirk of how stars die, while others argued we just lacked the tools to spot objects in this range. The unicorn, sitting squarely in that gap at 3 solar masses, suggests the latter might be true. Suddenly, the mass gap looks less like a cosmic rule and more like an observational blind spot. Yet the unicorn's discovery also brings new challenges. How does a star even produce such a lightweight black hole? Typical supernova either leave behind neutron stars or forge black holes heftier than 5 solar masses. One possibility involves stars stripping away layers before collapse through intense stellar winds or binary interactions, creating a diet version of a black hole. Alternatively, these small black holes might form through mergers of neutron stars, though current models suggest such events usually produce slightly heavier objects. The unicorn might even hint at exotic physics. Perhaps certain types of supernova can produce low-mass black holes under rare conditions we've yet to understand. Now imagine the implications if we find more of these hidden runts. Current estimates suggest there could be hundreds of millions of black holes in the Milky Way alone, but those numbers rely on assumptions about their mass distribution. If the unicorn has countless siblings, we might need to rewrite the galactic inventory and reconsider how we search for black holes entirely. Traditional methods like X-ray detection, which relies on black holes siphoning material from companions, often miss dormant systems. Gravitational wave observatories like LIGO, meanwhile, are tuned to catch collisions of much heavier black holes. The unicorn suggests we might need new techniques to eavesdrop on the universe's quietest predators. Perhaps the most tantalizing thought is what the unicorn means for our cosmic neighborhood. At just 1,500 light-years away, it's practically in our backyard. If such black holes are common, statistically there could be others even closer, possibly undetected because they lack a companion star to betray their presence. This doesn't pose any danger. Isolated black holes drift harmlessly through space, but it underscores how much we still have to learn about the invisible architecture of our galaxy. The unicorn isn't just a scientific curiosity, it's a key to a hidden layer of reality, one that's been hiding in plain sight all along. In 2019, astronomers scanning the sky with Australia's ASCAP radio telescope stumbled upon something no one had seen before: vast, ghostly rings of radio emissions stretching nearly 1 million light-years across, floating in intergalactic space like cosmic smoke rings. These oddities, now called odd radio circles or ORCs, don't correspond to any known object. They're invisible in optical, infrared, or X-ray light, detectable only by their radio glow, and they're so enormous that if one replaced our Milky Way, it would engulf Andromeda too. The real shock: these rings aren't static. They're expanding outward at speeds approaching 6,000 kilometers per second, as if some unimaginable explosion sent shockwaves rippling through the fabric of space itself. Initial theories pointed to galactic mergers, perhaps 2 massive galaxies colliding, their central black holes creating a shockwave that rippled outward. But there's a problem. Most ORCs don't sit near galaxy clusters where such violent encounters are common. Another idea involves starburst galaxies, where frenzied star formation generates powerful galactic winds, but again, the scale is off. These rings dwarf even the most energetic star-forming regions. Then there's the black hole hypothesis, supermassive black holes erupting in titanic explosions, blasting jets that carve out these radio bubbles. Yet no active galactic nuclei, the telltale signs of feeding black holes, appear at the centers of ORCs. The most tantalizing explanation lies beyond standard astrophysics. Some researchers speculate ORCs could be the fingerprints of entirely new phenomena, perhaps dark supernova, from exotic stars made of hypothetical particles like actions or quark matter. Others wonder if we're seeing the aftermath of a never-before-seen interaction between dark matter and magnetic fields, an invisible dance suddenly made visible. There's even a wilder possibility. ORCs might be the remnants of wormholes, their throats collapsed long ago, but their gravitational echoes still resonating across the cosmos. What makes these circles so haunting is their impermanence. Simulations suggest they should fade within 100 million years, an eye blink in cosmic time. That means we're catching them at a special moment, like stumbling upon footprints in sand just before the tide washes them away. New telescopes like the Square Kilometre Array aim to uncover hundreds more, potentially revealing whether these are rare anomalies or signs of a hidden layer of universal physics. For now, ORCs remain one of the sky's quietest, grandest mysteries, echoes of forces we've yet to name, written in radio whispers across the void. Imagine the universe as a balloon slowly inflating, with galaxies drifting apart like dots on its surface. Now picture someone suddenly pumping air into that balloon faster and faster, stretching the fabric of space so violently that eventually even the dots themselves would tear apart. This isn't science fiction, it's our reality. In 1998, two teams of astronomers studying distant supernova made a discovery that shattered cosmic expectations. The expansion of the universe isn't just continuing, it's accelerating. And whatever's causing this runaway push, we've named it dark energy, not because it's sinister, but because it's utterly invisible. Its nature hidden from every telescope and particle detector we've built. The simplest explanation lies in Einstein's own equations. He once introduced a cosmological constant, a sort of background energy woven into space itself, to keep the universe static. When Hubble proved the universe was expanding, Einstein called it his greatest blunder. But now, that same constant might be staging a comeback. If dark energy behaves like this constant, it means empty space isn't empty at all. It seethes with a faint, repulsive energy that grows stronger as the universe expands, creating more space to contain more dark energy in a self-feeding cycle. The math works beautifully except for one glaring issue. Quantum field theory predicts the cosmological constant should be 120 orders of magnitude stronger than observed. That's like calculating the weight of a marble and getting an answer heavier than the entire observable universe. This discrepancy has spawned wilder theories. Maybe dark energy isn't constant at all but evolves over time, a concept called quintessence. Picture a cosmic syrup thickening or thinning as the universe ages. Some models suggest it could eventually decay, reversing acceleration and triggering a catastrophic big crunch. Others propose it might strengthen, leading to the Big Rip, a scenario where dark energy overcomes all forces, shredding galaxies, stars, and even atoms in a final, violent expansion. But here's the twist. Current data from projects like the Dark Energy Survey show dark energy's strength holding eerily steady, neither growing nor fading. The most unsettling possibility: dark energy might not be a force at all but a sign we've misunderstood gravity itself. Modified gravity theories suggest Einstein's equations break down across cosmic distances, creating the illusion of acceleration when reality operates by different rules. Yet these alternatives struggle to explain all observations, leaving most cosmologists reluctantly embracing dark energy's mystery. What makes this enigma so urgent is its existential stakes. Dark energy dominates the universe's energy budget, yet we can't explain its origin, its consistency, or its ultimate effects. It's the ultimate cosmic wildcard, determining whether the universe ends in ice, fire, or something beyond our imagination. Upcoming telescopes like Euclid and the Vera Rubin Observatory aim to map its influence with unprecedented precision. Until then, dark energy remains physics' most profound riddle, a reminder that the universe's greatest mysteries aren't just in the stars, but in the empty space between them. The thin, rusty air of Mars holds a secret that has taunted scientists for decades: fleeting puffs of methane gas, vanishing almost as quickly as they appear. Since 2004, orbiters and rovers have detected this simple molecule in the Martian atmosphere, sparking fierce debate. On Earth, methane is often a calling card of life, produced by microbes and livestock. But Mars isn't Earth. This gas could be geological, seeping from ancient aquifers or volcanic vents. Or just maybe it's evidence of something far more extraordinary: microbes clinging to existence beneath the frozen soil of a seemingly dead world. The controversy centers on methane's stubborn inconsistency. Unlike Earth, where atmospheric methane persists for years, Mars's version comes and goes unpredictably. NASA Curiosity rover, sniffing the air in Gale Crater since 2012, has recorded spikes 60 times higher than background levels, only to watch them dissipate within weeks. Even stranger, the European Space Agency's Trace Gas Orbiter, designed specifically to map methane globally, often sees nothing where Curiosity detects plumes. It's as if Mars is playing a cosmic shell game, hiding its methane in plain sight. Geologists argue non-biological sources could explain the enigma. Methane might form when water trickles through mineral-rich rocks like olivine, a process called serpentinization that doesn't require life. Alternatively, ancient methane trapped in icy deposits called clathrates could be thawing sporadically, released by seasonal temperature shifts or meteorite impacts. Even micrometeorites raining down on the planet's surface might carry carbon-rich molecules that break down into methane under ultraviolet light. These scenarios paint Mars as a geologically active world, its subsurface whispering with chemical reactions we've yet to fully understand. But then there's the biological angle. Certain extremophile microbes on Earth thrive in Mars-like conditions deep underground without oxygen, consuming hydrogen and carbon dioxide while exhaling methane. If similar organisms exist in Mars's damp subsurface brines, they might produce methane in burps too faint and localized for orbiters to spot consistently. The case hinges on nuance. Biological methane often carries isotopic fingerprints, preferential weights of carbon atoms that differ from geological sources. So far, Curiosity's samples show ratios that could swing either way, leaving scientists parsing fractions of a percent for clues. The plot twists further with seasonal patterns. Curiosity's data reveals methane levels rise slightly during Martian summers, hinting at a temperature-sensitive source. Some researchers envision underground reservoirs pressurized by seasonal thawing, forcing methane through cracks like a planetary exhale. Others speculate dormant microbes might metabolize more actively when warmer. Either way, the cyclical nature baffles those expecting random geological outbursts. NASA Perseverance rover is now hunting answers with sharper tools, including lasers that can pinpoint methane's origin within a few dozen feet. Meanwhile, the ExoMars rover Rosalind Franklin, set to drill 6 feet below Mars's sterile surface, could finally settle the debate. Until then, each whiff of methane keeps alive a tantalizing question. Is Mars sighing with the last breaths of long-lost life? Or are we witnessing the slow, sterile chemistry of a world that never woke up at all? The red planet guards its secrets well, but not forever. Every gust of wind, every grain of sand might hold the key to knowing whether we're alone in the cosmos or just late to the party. Saturn's north pole hides one of the most precise geometric anomalies in the solar system, a colossal hexagon big enough to swallow 4 Earths, spinning like a cosmic gear for decades without breaking shape. Unlike Jupiter's Great Red Spot, a turbulent storm that shifts and fades, this 6-sided jet stream has endured since Voyager first glimpsed it in the 1980s, its razor-sharp angles defying the chaos of planetary weather. The hexagon doesn't just exist, it dominates, with winds screaming at 320 kilometers per hour, tracing its edges like an invisible draftsman's tool. How can something so rigidly geometric persist in an atmosphere of churning gases? The answer might rewrite what we know about planetary dynamics. At first glance, the hexagon seems to defy physics. Nature prefers curves, spiral galaxies, hurricane eyes, even the rings circling Saturn itself. Sharp angles typically emerge from human engineering, not fluid dynamics. Yet laboratory experiments here on Earth offer a clue. When scientists spin fluids in circular tanks, stable polygonal shapes, including hexagons, can form under specific conditions. The key lies in sheer velocity, where different layers of gas or liquid move at varying speeds, creating standing waves that lock in geometric patterns. On Saturn, this might mean the hexagon is a towering atmospheric waveguide, a self-reinforcing ripple propagating through the planet's jet streams. Imagine stirring honey with a spoon. If done just right, you'd see temporary ridges form. Now scale that up to planetary proportions with a storm system so vast it could stretch from New York to London, and you've got the framework of an explanation. But there's a catch. Lab models struggle to replicate the hexagon's persistence. Earthly experiments produce fleeting polygons that dissolve within seconds, while Saturn's masterpiece has outlasted human observation. This durability suggests deeper forces at play. Some theorists point to Saturn's interior, where differential rotation, the core spinning at a different speed than the outer layers, could generate resonant vibrations that stabilize the hexagon from below. Others speculate about the influence of Saturn's magnetic field, which might interact with charged particles in the atmosphere to sculpt the storm's edges. The most radical idea, the hexagon is a sonic artifact, literally a standing sound wave of planetary scale, frozen in time by the peculiar acoustics of Saturn's atmosphere. Then there's the mystery of depth. Cassini's infrared instruments revealed the hexagon isn't skin deep. It plunges hundreds of kilometers downward, a 3-dimensional structure with roots possibly anchored in Saturn's internal heat. This vertical dimension adds another layer of complexity, hinting that the hexagon isn't just a surface feature but a window into the planet's hidden workings. Like a lighthouse beam cutting through fog, its stability might be a side effect of deeper convective currents, a signpost pointing toward processes we've yet to understand. Perhaps the most haunting question isn't how the hexagon forms, but why it's unique. No other planet, not even Jupiter with its roiling storms, displays such a perfect geometric storm. Is Saturn's rotation rate or axial tilt just right for hexagonal resonance? Or is this shape a fleeting phase in the planet's climatic evolution, something that appears and vanishes over millennia? We may never know for certain. With Cassini's mission ended, our window into this phenomenon has temporarily closed, leaving the hexagon to spin in enigmatic silence. Until future probes return, it remains a cosmic work of art, painted in hurricane winds and etched deep into the fabric of a gas giant, a reminder that even the most familiar planets still guard astonishing secrets. Imagine an entire galaxy so faint, so whisper-thin, that it slips past telescopes like smoke through a screen. These are ultra-diffuse galaxies, cosmic phantoms where starlight barely clings to existence, their sprawling forms containing just 1% the stars of our Milky Way, yet spanning similar distances. They float through space like celestial jellyfish, their gauzy arms barely visible against the black. But here's the twist: some of these ghostly giants shouldn't exist at all. Packed into violent galaxy clusters where gravitational tides tear ordinary galaxies apart, they've somehow survived pristine and unscathed. Now astronomers face a haunting question. Are these delicate giants cosmic accidents, or do they guard secrets about dark matter we've yet to uncover? The first ultra-diffuse galaxy, Malin 1, was spotted in 1987, a smudge of light so faint researchers initially thought it was a faulty observation. Today, we've catalogued hundreds, and their peculiarities only deepen the mystery. Take Dragonfly 44, a galaxy in the Coma cluster with barely 1% of the Milky Way stars, yet emitting gravitational ripples suggesting it's 99.99% dark matter. That ratio defies logic. Dark matter halos are supposed to scale with visible matter, yet here's a galaxy that's essentially an invisible cloak with a few stars sprinkled on like glitter. How does such an object even form? One theory suggests they are failed galaxies, where normal matter was stripped away by intergalactic winds or collisions, leaving behind dark matter skeletons. Others propose they're the ancient cores of once normal galaxies, their outer layers shredded by cluster tides over billions of years. But the plot thickens with galaxies like NGC 1052DF4, an ultra-diffuse spectre with almost no dark matter at all. This discovery sent shockwaves through astronomy, challenging the long-held rule that dark matter is the universe's invisible scaffolding. If galaxies can exist without it, does that mean dark matter isn't as universal as we thought? Or could DF4 be the product of a violent encounter, a galaxy robbed of its dark matter in a high-speed collision, like a thief snatching a wallet without stopping? Simulations show such thefts are possible, but the odds of catching one in the act are astronomically slim. Even stranger are the ultra-diffuse galaxies thriving in cosmic war zones. The Coma and Virgo clusters, regions so dense with galaxies that gravitational chaos reigns, should be the last places fragile structures survive. Yet here they sit, intact as blown glass sculptures in a hurricane. One explanation invokes extreme dark matter density, halos so massive and tightly bound that they act like cosmic shock absorbers, protecting their scant stars from tidal destruction. Another idea flips the script. Perhaps these galaxies form directly in clusters, condensing from gas so turbulent it could only muster sparse starlight. The most tantalizing clue lies in their star-forming potential. While most ultra-diffuse galaxies are ancient relicts, a rare few flicker with newborn stars defying their ghostly reputations. These active exceptions, like the fluffiest galaxy known, UDG 32, challenge the notion that all diffuse galaxies are cosmic dead ends. Could they be incubators for a unique class of stars, spread so thin that supernovas rarely disturb their tranquility, allowing slow, steady stellar births over eons? Or are we seeing the last gasps of systems destined to fade entirely, as telescopes like JWST and Rubin Observatory turn their gaze to these enigmatic structures? Each discovery peels back another layer. Ultra-diffuse galaxies aren't just astronomical oddities, they're stress tests for our models of galaxy formation, dark matter's role, and the resilience of cosmic structure. Whether ancient survivors, dark matter anomalies, or something else entirely, they force us to confront a humbling truth. The universe crafts its mysteries in both the brilliant and the barely there, proving darkness and light alike have stories to tell. Every star will burn out, every galaxy will drift into darkness. The universe, as we know it, is on a one-way journey toward an irreversible fate, but what that end looks like depends on forces we're only beginning to understand. Picture a clock winding down, its gears slowing as the last grains of cosmic sand slip through the hourglass. The final act of the universe hinges on a tug of war between two invisible players: entropy, the relentless force driving everything toward disorder, and dark energy, the mysterious agent accelerating space itself apart. Depending on who wins, the cosmos could face oblivion in ice, fire, or something far stranger. Heat death is the most widely accepted scenario, a slow, silent fade into maximum entropy. In this future, trillions of years from now, the last stars exhaust their fuel, leaving behind frigid cinders, black dwarfs, neutron stars, and black holes. Even these remnants won't last forever. Over incomprehensible timescales, black holes themselves evaporate via Hawking radiation, their energy leaking away into the void until nothing remains but a thin, uniform haze of photons too weak to interact. The universe becomes a static, featureless graveyard where temperatures approach absolute zero and time loses all meaning, no energy gradients, no change. Just an eternal, unchanging stillness stretching endlessly into the dark, the ultimate triumph of entropy. But dark energy might have other plans. If its repulsive force continues strengthening, it could trigger the Big Rip, a far more violent finale. Imagine the fabric of space stretching faster than light itself, tearing apart galaxy clusters, then stars, then planets, until even atoms are ripped asunder. The very forces binding matter together would be overwhelmed, leaving a universe of isolated particles unable to ever interact again. Recent measurements from the Dark Energy Survey hint that while dark energy's strength seems constant now, we can't rule out future shifts. If it evolves into a phantom energy state, the Big Rip could happen sooner than we think, shredding reality in a cosmological blink. Then there's the specter of vacuum decay, an existential threat hiding in the quantum realm. According to quantum field theory, our universe might not be in the lowest possible energy state. Like a ball balanced on a hill, it could be metastable, waiting for the slightest nudge to roll into a truer vacuum. If this transition occurs anywhere, even a single point, it would unleash a bubble of true vacuum expanding at light speed, rewriting the fundamental laws of physics as it spreads. Atoms, forces, even space-time itself would reconfigure instantly, erasing everything we know. The chilling part, this could be happening right now in some distant galaxy, and we wouldn't know until the wall of doom was already upon us. Yet not all endings are bleak. Some models suggest a cyclical universe where dark energy eventually weakens, allowing gravity to pull everything back in a big crunch, a fiery collapse that births a new Big Bang. String theory even proposes our universe is one bubble in an eternal multiverse, where death in one realm means rebirth in another. The truth might be stranger than any of these extremes. With telescopes like Euclid mapping dark energy's influence and experiments probing quantum vacuum stability, we're inching closer to forecasting the universe's destiny. One thing's certain, the cosmos won't go gently into that good night. Whether it fades, fractures, or reboots, its final moments will be written in the very forces we're only now learning to measure. And in that grand finale lies a paradox. The same dark energy dooming the universe also illuminated our understanding of it, proving that even in endings there's revelation. From the cosmic undertow of the dark flow to the eerie silence of the Fermi Paradox, these 25 mysteries aren't just curiosities. They're cracks in the foundation of everything we think we know about the universe. Each one forces us to confront how little we truly understand, whether it's the Great Attractor's gravitational grip, the hexagonal storm on Saturn, or the ghostly whispers of missing baryons. These aren't just puzzles waiting to be solved, they're invitations to rethink reality itself. Consider how these enigmas intertwine. The same void that might hide dark energy could also explain the cold spot in Eridanus. The same physics-defying black holes like the unicorn might hold clues about dark matter's role in ultra-diffuse galaxies. Even the zodiacal light's excess glow and the red rectangle's perfect geometry hint at hidden processes shaping the cosmos in ways we're only beginning to glimpse. Every mystery peels back another layer, revealing just how much lies beyond the edges of our current knowledge. But here's the most thrilling part: this list is just the beginning. For every mystery we've named, there are countless others lurking in the data, anomalies dismissed as noise, signals too faint to decipher, or phenomena so strange we haven't even noticed them yet. The universe doesn't play by our rules, and that's what makes exploration so exhilarating. Maybe you're drawn to the spine-tingling possibility of extraterrestrial megastructures around Tabby's star, or perhaps the cosmic horror of vacuum decay keeps you up at night. Whatever resonates with you, these mysteries belong to all of us. They're not just for scientists in labs, they're for anyone who's ever looked up at the night sky and wondered. So let's keep questioning, because curiosity is the engine of discovery. Share your favorite theories in the comments. Do you think Oumuamua was a fragment of an alien world or just a cosmic oddity? Is the WOW signal proof we're not alone or a cosmic coincidence? The conversation doesn't end here. With new telescopes like JWST and the Vera Rubin Observatory coming online, we're on the verge of breakthroughs that could rewrite entire chapters of astronomy. The cosmos is vast, strange, and far from finished surprising us. Stay curious, keep looking up, and remember, the next great mystery might be hiding in plain sight, waiting for someone like you to notice.